Welcome. This is the Cisco CCNA3-ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Welcome to the Enterprise Networking Security and Automation version 7 curriculum. Module 2, Single Area OSPFv2 Configuration. In this video, we're going to be talking about OSPF router IDs, how to configure them. We're also going to be configuring a single area point-to-point OSPFv2 network. We're going to talk about multi-access OSPF networks. That will be bringing up like the designated router and backup designated router configurations and how to modify priority information. We're going to talk about how to modify a single area OSPF, how to implement those changes as well. We're going to talk about default route propagation, and we're going to talk at the end about verifying implementation of OSPFv2. So let's go ahead and let's jump right in. Let's talk about OSPF router IDs. So in this figure, we look at 3 routers. We see that they have the appropriate networks. This is a 10.10.1.0 network. This is a 10.10.3 network. This is a 10.10.2 network. And they have the appropriate subnet mask, or the networks and subnet masks between the routers. But in this network, there is no static routing, there is no dynamic routing, there is really nothing. So all the interfaces on R1, 2, and 3, except the backbones, should be within the OSPF area. The ISP router is used as a gateway of last resort, but this is going to be the sphere of our OSPF. You'll notice it says area 1. This is not in our gray color because this is outside the sphere of our area 0 control. So how do we configure OSPF? You do router OSPF and a process ID. Here the process ID is 10. That is basically just a way of denoting what all the routers will be using for their OSPF. And you'll notice that it is best practice to use the same process ID on all of the routers. So once you configure router OSPF, then you can notice it takes you down to the sub command, router tac or config tac router, and here's all the options we get. We're going to be configuring network statements in a little bit. Passive interfaces we'll discuss a little later in this video, but then we have this router ID. The router ID for this OSPF process allows us to configure our priorities using router IDs. So an OSPF router ID is a 32-bit value represented as an IPv4 address. It's used to uniquely identify the OSPF router and all of the packets, including the router ID of the originating router. So it's basically a way for us to flag what the router will be designated as. Each router requires a router ID to participate in the OSPF domain. It can be defined by the administrator or automatically assigned by the router. The router ID is used by the OSPF-enabled router to do 2 big things. Participate in the synchronization of the OSPF database. This is basically during the exchange states. The router with the highest router ID will send the database descriptor packet first. So again, the IDs will matter. Also, the ID allows the router to participate in the election of a designated router. If we're assuming a multi-access LAN environment, multi-router environment, the router with the highest router ID will be elected the designated router. The one with the second highest ID will be the backup router. So if we want to designate which router will become the primary or the designated router, we would set a higher router ID on that device. That allows us to dictate what device will get the designated router process. Alright, so router ID order of precedence. the router ID is explicitly configured using the router ID command. That would allow it to go first. The router will choose the highest IPv4 address of any configured loopback address. So if you don't manually configure a router ID, the router will choose the highest loopback address. If there is no router ID command issued and there's no loopback address, the third choice would be the router will choose the highest active IPv4 address of any of the physical interfaces. So router ID, if that doesn't happen, it will look at loopback. If that doesn't happen, it will look at physical address. And it's going to take the highest of them. And again, the purpose here is the highest IP address will become the designated router or the primary router within the OSPF environment. So that's the process for router ID selection. So how do we configure a loopback on a router? We do interface loopback, give it a number, and we treat it like a interface. So if we do a show IP protocol, we will get a router ID of our loopback. If we want to explicitly configure a router ID, underneath OSPF router and the process ID, we could issue a router ID command, and it will do that first. So what happens if we do a router ID under OSPF and we also do a loopback? Again, that order of operation, explicitly stated router IDs under the router OSPF process ID first. Next will be loopback. Next will be physical interfaces. So if router ID is configured underneath the first option, it will ignore the other options. So whichever one it comes across first with the router ID, that becomes the router ID. So again, understanding the order of operations there is kind of important. So how do we modify a router ID? So you can always clear the IP or the IP OSPF process, and then you can modify it. You can modify it, but once the router is processing the OSPF, the new router ID will not actually be updated. So you have to do the clear IP OSPF process to actually clear the process or restart the process to refresh the router IDs. So moving on, let's talk about how to configure OSPF in a point-to-point network. So again, OSPF or router OSPF, give it a process ID. That gets us to our config TAC router. Then we need to issue network commands. It will be network, the network ID, the wildcard mask or the inverse of the subnet, the area, and then the area ID. If we're talking a single area OSPF, this should be area 0. That's pretty common. The area ID syntax will refer to, the OSPF area. If we're talking single area, it would be 0. If we're talking multi-area, which we'll talk later in this video about that, it would be a different area. So again, the subnet mask is going to be, let's say, a /24, so 255.255.255.0. The wildcard mask is the inverse of the subnet mask. So /24, 255.255.255.0, the inverse would be 000.255. If we're talking a /26, again, I don't know why the diagram is like that. A /26 would basically take the 26 ones, and the remaining ones would be 6 zeros. You flip all the ones to zeros, you flip all the zeros to ones, and that would be your inverse. Again, inverse is just a clever way of saying take your subnet, and the opposite of the subnet would be your inverse or your wildcard. And that is how we get our network and wildcard masks. So here we have our 3 network statements. This will be whatever networks are attached to that router. So earlier we had our connections between routers 1 and 2, routers 1 and 3, and we had our LAN. So 10.10.1.0 with a /24, so the inverse would be 0.0.0.255. So again, that's how we do our calculations for our wildcard masks. And you would do that for each of the routers. You can also explicitly state what the addresses are with a wildcard mask of straight zeros. Basically, it says use that specific interface, so whatever IP address that is applied to that interface, that will be the interface processing those OSPF commands. That basically just says you don't have to worry about the wildcard masks, so you can do quad zeros. Realistically, you should get used to doing the wildcard masks. And you'll notice these are the specific addresses of those interfaces, not the network IDs. So let's try to put this together as a whole. How do we configure OSPF? Again, OSPF, we would do the network statements, or we could do the network statements underneath the interfaces. So here we have a ISPF or IP OSPF process ID. We could give it an area, and we would then navigate to the different interfaces. So you'll notice here we have one for our loopback, our gig 001, and our gig 000. So you can do the OSPF underneath each interface, or you can do it underneath a explicit router statement. It just kind of depends on what you want to do. So you do not need to do the network statements if you're doing it underneath each interface. But if you do it underneath each interface, you need to make sure to do it underneath all of them. By default, OSPF messages are forwarded out all OSPF-enabled interfaces. So even if you do not want it to send OSPF updates out of the LAN, by default, it will. The problem is, by sending it out all interfaces, sending it to the LAN, for example, that is a higher security risk. Also, sending it out all interfaces is an inefficient use of resources and bandwidth, because again, the LAN doesn't really need to receive those updates. The fact that the LAN could get an update means the LAN could also respond. So if you have a malicious person on a LAN, they could send router updates if the OSPF is listening on that LAN interface. So we have what's called a passive interface, basically saying do not send or receive updates on this interface. And you normally will do that on LAN interfaces. So how we do that is basically say passive interface, and you give it whatever interface you do not want to send updates to. Normally you do not want to update the loopback, and you do not want to update the LAN addresses. You can now verify by doing a show IP protocols command to verify which interfaces are passive. And you'll notice here, show IP route, it will show us the information like router ID, maximum paths. It will show routing on the interfaces explicitly, and it'll also list where the passive interfaces are located. Here we only have the loopback as passive. So we can also then look at further details by show IP OSPF, going to the appropriate interface, and you could drill down on additional information that way. You can see things like its designated router ID, the interface ID. You can see what its current router ID is, its backup ID. So from this information right here, we can tell that this is our router ID, and you can tell that we are the backup designated router because that's our router ID information. So again, show IP OSPF interface gives us details specific to those interfaces. To change this to a point-to-point network using the interface configuration command, we could do an IP OSPF network point-to-point on all of the interfaces where you want to disable the designated router, backup designated router election process. If it is just a point-to-point, like between a one router and another router, and there is no additional connectivity or an additional connection there, you can set just a point-to-point, and you could do that underneath the interfaces. So again, interface gigabit 000 IP OSPF network point-to-point, that disables the designated router, backup designated router election process. Thus, you don't have to worry about it consuming resources. It consumes resources because this is done via a broadcast. So let's go ahead and let's talk about the use of loopbacks to provide additional interfaces for a variety of purposes. To simulate a real LAN, you could use a loopback interface. So if you do a show IP route and include our loopback address, you can. We can see that when R1 advertises its loopback address, that is what we're getting. We're getting that /32. So if we configure a loopback interface and we configure it as a point-to-point connection, then we will actually get the appropriate subnet mask. Because again, by default, the loopback interfaces are advertised as a /32. We do have a packet tracer lab for you to configure the point-to-point. Moving on, we have our multi-access OSPF network, which is not point-to-point. These are going to be, again, via broadcast. So another type of network that uses OSPF is, again, multi-access. Here we're talking about the distributions of link state advertisements, also known as LSAs. The router that is elected for the role should be determined by the network administrator through proper configuration, as opposed to a election. Hence the setting the appropriate router IDs so that the administrator can properly set which router will become the designated router. Again, multi-access network, OSPF will elect a designated router and a backup designated router. Again, the DR is responsible for collecting and distributing LSAs sent and received. The DR will be used for a multicast IPv4 address. It will use 224.0.0.5, which is basically a clever way of saying all OSPF routers on that network. So the primary designated router will be the one that's going to be sending and receiving the LSAs. If the designated router fails, a backup will kick in, hence the BDR. Because again, the BDR will listen passively. It will also maintain a record and a relationship with all routers and routes, so that if the DR does stop producing hello packets, the BDR can kick in immediately. If you are not a DR or a BDR, you will be known as a DR other. This is essentially a router that's classified as an other than designated router. And DR others will use the multicast address of 224.0.0.6. Again, all designated routers to send OSPF packets to the DR and BDR, while only the DR and BDR will listen for the 224.0.0.6. So again, here the DR other will send that multicast address, and that's a clever way of saying to send to the DR and BDR. In a multi-access topology, here we have 3 routers connected to some form of layer 2 network. Because the routers are connected over a common network, OSPF has automatically elected a DR and BDR. Here, if we are looking at the router IDs, the highest router ID will become the DR. The second highest will become the backup DR, or BDR. To verify the roles, we can again do a show IP OSPF interface, and you can see the designated router and the backup designated router IDs, as well as your current router ID. So again, R1 has two adjacencies, one with the BDR and one with the DR. You can see that here's the neighbor count, adjacent neighbor count, and you can see the adjacent neighbors. 2222 is the ID and 3333 is the other ID, and it will actually list as backup DR and DR. So the output is, this is looking at the output for R2. You will notice that it also has two neighbors. The adjacency with neighbor 1111, it does not have a name because it would actually be a DR other, and it has the adjacency to 3333, which is the DR. You can also see its router ID. You can see the designated router and the backup designated router right here. It will provide additional information, but this is the key stuff that we need to look at. If we look at R3, again, R3 is connected to 1 and 2, and same thing like the other ones, it will list the designated routers, the backup designated routers, and it will list the adjacencies and any important information about those adjacencies. Here, with the neighbor being 2222, its important information would be that it is part of the backup designated router, and that is it. So again, looking at show IP OSPF interface, you can see the router ID, you can see the router state, you can see the priority, you can see the adjacencies, and you can see which routers are classified as the DR and BDR. So how can we verify the DR and BDR and their adjacencies? We need to do the show IP OSPF neighbor command, and they should state a few different things. It should be a full druther, a full DR, a full BDR, or a two-way druther. Basically, a full druther, this is when a DR or BDR router that is fully adjacent with a non-DR or non-BDR router. These two neighbors can exchange hello packets, update queries, updates and queries, and update queries, replies, and acknowledgements. A full DR, the router is fully adjacent with the indicated DR neighbor, with two neighbors can exchange hello packets, updates, queries, replies, and acknowledgements. A full BDR, again, full adjacency, indicating the BR neighbor. These two neighbors can exchange hello packets, updates, queries, replies, and acknowledgements like the other ones. A two-way druther, these are when the two non-DR or BDR router has a neighbor relationship with another non-DR or BDR router. They can exchange only hello packets. Because again, the goal here is to have the DR other exchange hello packets, updates, queries, replies, and acknowledgements only with the DR and BDR. So if it's seeing its neighbor as a DR other, it can only send a hello packet, nothing else. The normal state for an OSPF router is usually full. If a router is stuck in another state, it could indicate that there's a problem forming the adjacencies, and only exception to this is a two-way state, which is normal in a multi-access broadcast network. So again, if we have multiple routes, it's going to be either a full or a two-way druther. Verifying the adjacencies, if you do a show IP OSPF neighbor, you can actually see the state, what they are. Again, full druther versus full DR, we need to understand the different states, and a two-way. Again, if we have multiple routers in a string, the designated router is the only one, and the backup designated router, those are the only two that should be getting multiple packet types. Everything else should only be getting hello packets. So now let's understand the election process. So the DR and BDR election is based on the following criteria. First, the router in the network will elect the router with the highest interface priority as the DR. The second highest priority will become the backup designated router. So you can manually configure a priority between 0 and 255. If the interface priority is set to 0, the interface cannot be elected as a DR or BDR. The default priority of a multi-access broadcast interface is 1. If the interface priorities are equal, then the router will use the highest router ID. So router ID is actually not the first option in our election process. We can set priorities. If we do not set priorities, it will use the default priority of 1, and then it will use the router ID. The election process will take place when the first router with the OSPF enabled interface comes online. It will start pairing with its neighbors, creating adjacencies, and trying to elect which one will become the designated router. What's really funny is I used to cover this way more in depth. Basically, when two OSPF routers come online, they elect themselves as DR. As they start exchanging information, whoever has the higher router ID becomes the DR, and then the other one will actually unelect themselves and then elect the highest router ID as the DR. But as we add additional routers, the new routers do not always initiate a new election process. So unless we're clearing our OSPF process, if we add in additional routers, the election process will not repeat itself. Again, the way this is set up, so is if the DR does fail, then there should be a backup DR that should then take its place. So after the DR is elected, it will remain the DR until the DR fails. The DR actually has a process restart, or if the DR interface is shut down, that will actually then prompt the BDR to automatically promote itself to a DR. Again, however, after the BDR is promoted to a DR, a new BDR will be elected, and then the druthers with the highest priority of the ID will be elected that new BDR. So if the DR, the original DR that failed, does come back online, it does not take its DR status back unless a new election is then forced. So IP-OSPF priority command, what we do is we issue the IP-OSPF priority space value command, again between 0 and 255. 0 cannot get a BR or a DR or a BDR state. So where do we issue this? We issue this underneath a interface, and then we can clear the OSPF process to initiate an election. And we actually have a lab doing this. So moving on, how do we modify a single area OSPF? So let's look at the metric that OSPF uses. OSPF uses a cost metric, and the cost will be the reference bandwidth divided by the interface bandwidth. The default reference bandwidth is 10 to the 8 power, or 100 million. Therefore, the formula should be 100 million bits per second divided by the interface bandwidth in bits per second. So because the OSPF cost value has to be an integer, things like fast Ethernet, gig, and 10 gig share the same cost. So you can actually modify this by doing an auto cost reference bandwidth so that we can get different values. And what I mean by that is, because again, fast Ethernet, gig, 10 gig, they're all set to 1, even though realistically they are not the same. So by doing the adjustment, we can get the appropriate bandwidth. And again, the cost value has to be an integer, so if we actually do this, we should not be getting 1 for everything. 0.1 is 1. 0.001 is still 1. So that's one of the reasons why that cost analysis, or that cost adjustment. To assist OSPF in making the correct path determinations, the reference bandwidth must be changed to a higher value to accommodate the faster networks. So anything faster than 100 megs. Again, in reality, 100 megs used to be fast, 20 years ago. It's no longer the same, so adjustments had to have been made. So by changing the reference bandwidth, it does not actually affect the bandwidth capacity. To adjust the reference bandwidth, we could use the autocost reference bandwidth in megabits per second router command. So we can actually set a 10 gig link by doing an autocost reference bandwidth 1000. If we want, that would be our gig. If we wanted 10 gig, it would be 10,000. To return to the default, we would set it back to 100. 100 is again just 100 megs. Another option to change the cost on one specific interface is using the OSPF cost command. So we can adjust that. So how does the reference bandwidth chart look now when we've actually modified it? So now we're looking at when we see 10 gig, cost would be 1, gig would be 10, a 100 megabit would be a cost of 100. That way we have more an appropriate cost so that OSPF can use the appropriate cost values to actually do the forwarding. The cost for OSPF routes should be an accumulative total between them. So if we want to go from here to the internet, it would be cost 1, cost 10, and over. If we want to go route 1 to route 3 to route 2, it'd be cost 1, cost 10, cost 10 again, and to the internet. So here would be a cost of 20, here would be a cost of just 10. The lower the cost, the better. So this would be the preferred path for this connection. This would not. However, if these were 10 gig links and this was just a gig link, then the preferred path would actually be R1 to R3, R3 to R2, R2 to the internet. But that's assuming these were 10 gig links and the costs were adjusted. So how do we see that as a number? So again, here we have 1 plus 10. That cost total is 11. This cost would be 1 plus 10 plus 10 internet. So this would be 21. So verifying the accumulated cost for a path, you could actually look at a IP route and you could see the cost or the metric used. So again, we have a metric of 11 because we have the cost to go from this PC to the router, from the router to router 2, and so that'd be 1 plus this cost of 10. That's how we get that 11. The lower the metric, the better. So reasons to manually set cost value is if you actually want to control the flow of traffic through the network. Connections to the equipment from other vendors could also be an issue, or if they're using different routing protocols. So test failover to a backup route. We can always verify by adjusting the cost of one route to verify that a backup route actually kicks in. And you'll notice here we have our backup route values. You'll notice the metrics are higher. So let's talk about our hello packet intervals. OSPFv2 uses hello packets, and again they're transmitted to a multicast address 224.0.0.5. That's all OSPF routers, and this is done every 10 seconds. You can modify the default timer if you wish. The hello packets are not sent on passive interfaces, typically the LAN. So, yeah. The dead interval is the period of time that the router will wait to receive a hello packet before declaring the neighbor down. If the dead interval does expire before the route receives a hello packet, then the OSPF will remove the neighbor from its database. The router will flood the database update to all of its neighbors. Cisco will use a default of 4 times the hello packet interval. So if the router does not receive a hello packet from its neighbor within 4 times the normal hello interval, then it will declare it's dead. So Cisco uses the default of 4 times for the hello interval. This is basically 40 seconds on a multi-access or point-to-point network. So how do we verify hello and dead intervals? If we do a show IP OSPF interface, we can look at the timer intervals. We can look at the hello, the dead, the wait, the retransmit, and the resync numbers. In the CCNA, we're mainly focused on the hello and dead timers only. So we can also do a show IP OSPF neighbor, and you can see the dead timer. And again, by default, this value is refreshed every 10 seconds. When the router receives a hello packet from the neighbor, it will refresh the dead timer. So how do we modify the intervals? Underneath the interfaces, we could do an IP OSPF hello interval and the number, or a dead interval and the number. You can also then remove them by doing the no IP OSPF hello or dead interval command, and that would reset them back to their default values. In this example, we've modified them to 5 seconds and 20 seconds. And again, the dead timer has to expire in order for the routes to be classified as dead. We have a packet tracer lab modifying these values to verify retention of that information. So going on, we have section 2.5, the default route propagation. This is basically how to propagate a default route from one router to everyone else. So if we have a default route, for example, we set a IP route for 000, 000, we send it out loopback 1. How do we propagate that route to everyone else? In OSPF, we have a command called default information originate. That will allow us the propagation of the default routes. Again, IP route should be quad zeros, space quad zeros, the next hop or the exit interface. If we issue the default information originate command, this will instruct the other routers to be the source of the default route. So if we have 3 routers and router 2 says, I have a default route to the internets, I can propagate that route to my neighbors, to router 1 and router 3, by using the default information originate. And we have a lab doing this. So how do we verify the propagation? You should see on R2 would be a static star. Star denotes a default route. S denotes a static route. Here we have a OSPF learned E2. And this is just a clever way of saying that this is a OSPF learned static route that's a default route and how to send it. And this is sent to router 2. E1 and E2 is beyond the scope of this module because again this is a higher level routing concept, but for our understanding it's again just basically stating send to router 2 because router 2 is propagating that default route. We do have a lab covering default route propagation. 2.6 is about verifying single area OSPFv2 and a review of those show commands. Again, show IP OSPF, show IP OSPF neighbor, protocols, and interface. These will all give us very specific information that we need to understand when we're looking at and troubleshooting OSPF. So again, show IP OSPF neighbor will verify the router has formed adjacencies, and it will give us our router IDs it will give us our states, it will give us our dead times, and it will give us our addresses. And if we have priority set, it would give us those as well. If two routers may not form an adjacency, again, it could be wrong subnet, it could be mismatch hello and dead timers, maybe the network types don't match, or incorrect OSPF network commands. So we need to be able to understand how to fix those. So doing things like show IP protocols, that will give us things like our routing protocol ID, it will give us our router ID, it will give us our interfaces, and it will also let us know if those interfaces are in an area or not receiving hello packets because you might have accidentally set them as passive. So those are all good reasons to use the show IP protocols command. If we are looking at show IP OSPF, that gives us again our OSPF, our process ID, our router ID, it will give us our area 0, and it will give us how long our algorithm has been functioning, and it will give us our reference bandwidth and things of that nature. Though this is more in depth, and this is actually outside the scope of the CCNA. Show IP OSPF interface will show us our process ID, our router IDs, our network types, our cost, and the adjacencies that we have formed. If we want to just do a quick overview, we could do a show IP OSPF interface brief, and that will show us our interfaces, our process IDs, our areas, our addresses, our costs, our states, our neighbors as well. And you'll notice the chart is not always lining up correctly because of spacing, but this will be our costs, this will be our state, and this will be our neighbors. We have a packet tracer doing all of our troubleshooting as well. And that is this chapter in a nutshell. Don't worry, we have another lab configuring things like point-to-point and our multi-access networks as well. We have a lab doing our configuration. So what we learned in this lesson is how to enable OSPF, how to issue route commands, how to issue network commands, how to get it functioning at a very basic level, how to control what interfaces get hello updates, how to turn some interfaces off so that they don't get hello packets, how to stop our election process, what the election process is, how the election process is set up and how it initiates, and how the different neighbored routers actually communicate with one another using multicast addresses. We learned about point-to-point and multi-point networks. We learned about priority values and setting up router IDs. We looked at costs and interface costs, as well as modification of our hello and dead timer intervals. We learned about basic OSPF, and we learned about our route propagation. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.